So in section 5.2 we were working with sums like this, and let's kind of recall what this represented. What we were doing is we were trying to find the area underneath a curve by using a bunch of rectangles. So we divided up that curve into a bunch of subintervals, and then at each subinterval we found the height of the rectangle by plugging a value of x into the function. That will give us the height times the width. Add up all those areas and we had an approximation to the area underneath the curve. Okay, so this looks like a rather poor approximation. What you could do to make your approximation better is to add more rectangles. So let's do that. Let's add more rectangles. And another way to express the fact that n is going to infinity is to express that the width of these rectangles is going towards 0. And as you add more and more and more, you get closer and closer to the true area underneath the curve. So that's what we were working with last time, something like this. Now as the length of those subintervals, the maximum length of those subintervals goes to 0, that's the same as n goes to infinity for us. What we're going to get is the area underneath that curve. And I'm going to define that area with the following notation. It's going to be the integral from a to b of f of x dx. Now a and b are the left and right hand endpoints along the x-axis of the area where you're trying to, of the area you're trying to find. With that definition then, let's look at a couple problems here. Starting with problem number 10. The limit as the maximum length of our subintervals, as the norm of our partition goes to 0, of the sum from I equals 1 to n of 6 times c sub I times 4 minus c sub I squared times delta x sub I. That limit, taken over the interval from 0 to 4, can be represented with a nice definite integral. It's a definite integral because I've got numbers here and here, as opposed to the stuff we worked with in section 5.1, which didn't have numbers. Those were indefinite integrals. This becomes 6x times 4 minus x squared dx. And I would appreciate it if you include the differential here on all of your integrals. I know that it seems like more of a pain than not, but there are a few instances where we need that. So we start out with this. We replaced it with an equivalent expression, which is our integral. And that's it. That's all we're looking for in problem number 10. This is your answer.
That was easy.
Yeah. Let's try a different one like that. It's problem number 14. Tell you what, let me give you a geometric perspective on what we just looked at. So our function here was 6x times 4 minus x squared, and we wanted to look at that for 0 to 4, so we're okay there. Let's zoom out a little bit, and then y max, let's go up to 50. That's pretty good. So what you're trying to find there is this area. The area that's shaded in blue, and actually shaded exactly in blue, not approximated with a bunch of rectangles. The approximation is kind of a step on the left-hand side. The right-hand side would be the limit as n goes to infinity. So if I were to replace this with something much bigger, say a 500, and then zoom up to 500, yeah, that's looking better. That's what we're looking for, is that area. And that's what's represented by our integral, by our definite integral. Let's try a different one. Kind of the same idea. The sum as the length of the partitions goes to 0. It is the norm of the partitions, or the maximum length. Sum, actually, you know what? I want limit of the sum from I equals 1 to n of 2 to the negative c sub I times the sine of c sub I times delta x sub I. And this time we're going to take that over the interval 0 to pi. What would that look like in terms of an integral? Now, Charlie? Mm-hmm. Yeah. dx. Good, and I appreciate the dx. Thank you. Especially in a problem like this where there's really no calculation at all, I definitely want to see the dx. So, cool. How do you figure that out? That's a great question. We don't have the answer to that. That answer is coming in section 5.4. Right now we're building up some of the notation so that we can get to the fundamental theorem of calculus. And this is part of that notation, is understanding the connection between this and that limit. Let's try some more here. This time we're going to start out with a graph and then move towards the actual integral. So let me try it this way so we can actually see something here. Let's do, the function is going to be 4 over x squared plus 1. And we want to go from the limit of, say, negative 1 to 1. So negative 1. Let's see if I can make a stop there. Sit. Stop. All right, let's just cheat here. Negative 1. There we go. Negative, whoa, it wasn't negative 1. There we go. There's negative 1. And up here, I want to go to 1. Perfect. So this is what I'm looking at. This is the area that we're dealing with. Let's see if we can write an integral that corresponds to this area. So we know the function. So the function is 4 over 1 plus x squared. So this is problem number 20. 4 over 1 plus x squared. How would I represent the area underneath that curve between those two limits? Anyone? Let's go back here. Let's take a look at this curve. So I'm going to integrate the function between negative 1 and 1. So it's going to be the integral from negative 1 to 1 of the function dx. And that's it. There's your answer. Yeah, that's it. That's all there is to it. It's just understanding that those areas now correspond to definite integrals. So the limits on the definite integral, where do those limits come from? Yeah, the graph. It's the edges of your area, right? And then the function was your integrand, and then you're integrating with respect to x. Giselle? All right, so going back to the last one, basically I'm replacing this function, which depends on c sub I. C sub I is the point in each of our subintervals where you're evaluating the height of the rectangle. I'm replacing that c sub I with x. So here's a c sub I. Now we have a minus x. Here's c sub I. Now we've got an x. Instead of delta x sub I, we've got dx. So it's just kind of a direct correspondence and replacement. What this represents is the area underneath this curve between 0 and pi and above the x-axis. So it's that area. In fact, if you'd like, let's take a quick look at the graph here for that last one. So let me change up my function. It'd be 2 raised to the negative x times sine of x, like that. And now I have to change my limit of integration. The last one was from 0 to pi. So it'd be from 0, 0. And let's zoom in up to pi, which I'm not going to be able to get on this one, but we'll go up to 3. So there's the general idea here, is it's this area. I'd probably change the view on that a little bit if I wanted to make it a little bit nicer. Okay, let's try a different one. Problem number 22. It's basically the same thing. And maybe this time, instead of going to decimals, we'll just look at it right in the book. So problem 22 looks like this. We've got this shaded area. We want to represent this shaded area using an integral. What integral would you write to correspond to that shaded area? 0 to pi over 4. What's the integrand? Tangent of x, dx. Good. So, problem 22. The integral from 0 to pi over 4 of tangent of x dx. And that's it. Done. You don't necessarily need parentheses. I put parentheses around this one. You know, I could put parentheses around this one. It's just to kind of keep your function in the differential straight. But you'll also see me write things like this. Negative 1 to 1 of 4 dx over 1 plus x squared. So it's fine. As long as that dx is there someplace, I'll be happy. All right? Okay. Well, let's keep going here. What you're seeing here is a nice correspondence between these definite integrals and areas. And we can take advantage of that correspondence in actually calculating things. Things like problem number 28. In problem 28, we've got the integral from negative 4 to 6 of 6 dx. Let's see if we can't help ourselves understand what that is. Now the integral is really this function, y equals 6. What's the graph of y equals 6 going to look like? Yeah, it's just going to be a horizontal line. So let's graph that. So something, like that, roughly speaking. So from negative 4 to 6, really what they're looking for is this area. And I don't think we necessarily need to have calculus in our toolbox of mathematical tricks in order to find this area. What's the area of that shaded region? 60, right? It's the height here times the width. So 6 times 6 minus negative 4 is the width, or 6 times 10 is 60. Nice. So again, nice correspondence between the area and this integral. 60. Let's try another one like that. It's problem number 32. Now as we move into problem 32, let me give you a reminder of a formula that you probably don't use all that often. So I like to remind people of these things as needed. And that is the area of a trapezoid. So here and here. I'm not trying to make this too even. Now what makes a trapezoid? What's characteristic of a trapezoid? Two of the sides are parallel. And you got some kind of a height here. Does anyone remember the formula for the area of a trapezoid? I got B1 and B2 and then the H. Close. Times height. Yeah, so let me write it this way. H over 2 times B1 plus B2. That's the area of a trapezoid. let's keep that in mind as we look at problem number 32. It's the integral. You know what? I'm going to go with the same number that I used in my morning class. The integral from 0 to 2. I think the book says 3. Is that right? All right, we're going to go with a 2 there. 0 to 2 of 8 minus 2x dx. So they're asking us to consider an area here. Let's draw this area and see what we can figure out about it. I think the analysis when the upper limit there is 3 is not really going to change much. This is really going to be the graph of y equals 8 minus 2x. That's going to be a line that slopes downward with a slope of negative 2. Y equals 8 minus 2x. What's the y-intercept of this function? Y-intercept. 8. Yeah, the other side will be 4, because if you plug in a 2 for x, you'll get a 4 for y. So maybe that's what you're giving me. I want to find this area in here. This shaded region right here. Here. What's the shape of that shaded region? It's a trapezoid. Now, if you're stuck on a test and I'm really mean and I don't give you the area of a trapezoid, look, you can just do it this way. You can break it up into the area of a triangle and the area of a rectangle, right? Just calculate those two. I assume you do know the area of a triangle. But that's all right. Let's do it as a trapezoid. So the height here, or excuse me, one of the bases is 8. What's the height of the other base? 4. And h is going to equal 2 in this thing. So the area here is going to be 2 over 2 times 8 plus 4 gives me 12. So we managed to calculate the area of this thing, even though we don't know the fundamental theorem of calculus just yet. It's coming, though. It's coming. How are you looking on problem 32? All right. Two is the height, so it's the h. So it's a different, h is the distance between, the perpendicular distance between the two bases. So I had a base here, right there, and I had another base right here. They didn't really give you it, but they gave you the limits of integration, which were 0 and 2. And when you plug in an x equals 0 into that function, you get y equals 8. If I plug in an x equals 2 into this function, I get y equals 4. So the heights there are basically just the y values when you evaluate the function at those points. Plug in a 2 in here, you get a 4. Plug in a 0 in here, you get an 8. The next one's going to be a little more challenging. It's problem number 36. The integral from negative r to r of r squared minus x squared dx. Boy, that looks kind of intimidating. It's a little less intimidating when you understand what this function is, what the integrand really represents. So let's consider the graph of y equals the square root of r squared minus x squared. Now, if you don't recognize what this is yet, you're not alone. I guarantee it. To make this a little bit more recognizable and easier to work with, let me square both sides of the function. So we get r squared equals, excuse me, y squared equals r squared minus x squared. Okay. And there's one last thing I'm going to do so that you recognize it. And I'm going to move the x squared to the left-hand side. So x squared plus y squared equals r squared. Can anyone tell me what that is now? Yeah, it's a circle, radius equal to r, and as a center at 0, 0, centered at the origin. So basically it's just the top half of a circle when you take the positive square root here, like we did with the current problem. So my goal is to find this area. What's the area of that region going to be? Well, what's the area of a circle? Pi r squared. So what should I write for this area then? 1/2 pi r squared. And that's it. It's just half the area of a circle is what you're getting. Are we okay with this? Again, the idea here is to build this correspondence between these definite integrals and areas. Now there's more to the mechanics of working with the definite integral than just understanding that, all right, this represents an area. The definite integral shares a lot of properties with the indefinite integral. Now one of them I'll illustrate after I show you some of the next problem. So for the next several problems, the next 4 to be particular or specific, they give you this information. The integral from 2 to 4 of x cubed dx is 60. The integral from 2 to 4 of x dx is 6. And the integral from 2 to 4 of dx is 2. So this is the given for the next 3 problems. We can use this information en route to solving problems 38 through 44. With the very first one of these, we're going to have to think a little bit outside the box, though. But we'll take a look at its graph, see if that can't help out. The first one is problem 38. They asked us for the integral from 2 to 2 of, I think it's x cubed. Is that right? Yeah, x cubed. Of x cubed dx. And I want to look at that graphically so that we can help figure that out. So let's change our function here. X cubed. So currently, in looking at this, I've got as my lower limit 0 and my upper limit 3. Well, the lower limit that we want here is supposed to be 2. So let's make that a 2. All right, so there's my lower limit. And let's see what happens when I change my upper limit. Now, right now, I'm trying to find the area underneath the curve between 2 and 3 and above the x-axis. But let's see what happens when I move this upper limit from 3 down to 2. How much area is left? None. Basically, when the upper limit and the lower limit are the same, you're trying to find the area underneath the point. So the calculus term for none, in this case, is 0. There's no area underneath a single point. I can put any function I want here, as complicated as I want, and if the limits are the same in both the lower limit and upper limit, the answer is going to be 0. Let's try problem number 40. And here we're going to start using some of what we have up above. the integral from 2 to 4 of 25 dx. Well, just like its cousin, the indefinite integral, the definite integral has linearity properties, meaning I can factor out a constant like this. So this is the same as 25 times the integral from 2 to 4 of dx. I can factor this out because it's independent of the variable here. It doesn't depend on x. So we'll factor that out. But that's helpful. How does that help me calculate the answer in problem number 40? Yeah, this much is given. So this is really 25 times 2, which is 50. Yay. There's your answer. Let's try a couple more. Problem number 42. The integral from 2 to 4 of x cubed plus 4 dx. What would you guess is going to happen here? What do you think I'm going to do with this? Break it up. Oh, good choice. Yeah. Let's break it up. 2 to 4 of x cubed dx plus the integral, actually 4 times the integral from 2 to 4 of dx. So again, using those linearity properties of the integral. And I know the first one, right? First one is 60. The second one is 4 times 2 for a total of 68. Problem number 44. The integral from 2 to 4 of 10 plus 4x minus, was it 3x cubed? dx. Yes? Oh, that was given, right? The integral of x cubed from 2 to 4 is 60. Thank you. Let's split this one up like we did with the last two. So this is going to be 10 times the integral from 2 to 4 of dx plus 4 times the integral from 2 to 4 of x dx. Notice I could take out the 4 because the 4 doesn't depend on the variable x. The variable x itself stayed in the integrand. Minus 3 times the integral from 2 to 4 of x cubed dx. We can now substitute in values for each of these integrals. Each of these integrals has a nice value given for it. Here, that was just a 2. Here, what was the integral from 2 to 4 of x dx? 6. And the last one, we've already used this one. The integral from 2 to 4 of x cubed was 60. So that's 20 plus 24 minus 180 is, I think, what, 136? Negative 136. Nice. How come do you suppose we got a negative number in this case? What do you think is going on that we got a negative number? Perfect. Some of the graph lies below the x-axis. Let's take a look at that. So this is going to be 10 plus 4x minus 3x cubed. And let's change our limits. Limits now are from 2 to 4, so we're okay there. Need to make this one a 4. see if I can get lucky, move that to 4. There we go, perfect. Wow, did I copy that right? I guess so. All right, so the area in this case lies below the x-axis. When you find these definite integrals, the value really reflects assigned area. So if your curve lies above the x-axis, you're going to get a positive value. If it lies below the x-axis, you're going to get a negative value. Area itself is always positive. We just call it assigned area because depending on if your curve is above or below the x-axis, then you'll get a positive or negative answer. In this case, we got a negative answer. So not a big surprise here given what we see from the function. Another one kind of like that would be problem number 46. Before I move on to 46, are we okay with these? Giselle?
How'd you get 0 the first one? Because I think you're just substituting them in.
Yes, so we're just using what's given. So these are the given values for all of these problems in this little section of the homework. So I just substituted these in. So the first one was 60. I substituted in, First one was 2. I substituted that in here. The next one was for x dx was 6. I substituted that in here. The last one was the 60. But all those values were given, and then I just substituted them in here respectively.
That makes sense. But what about the capital one, number 38? Where'd you get the 0 from? You showed it last.
Oh, well, yeah, the last one, in fact, there's a few properties in, and I appreciate the question because it's a reminder for me to go back and show a little bit about some of these properties. That one in particular, let's see, yeah, is on page 307. So one of a couple properties of the definite integrals. And this first one is if the limits, upper limit and lower limit, are the same, you're going to get 0. Okay. Another property, and we'll be able to better understand this after the next section, or at least the beginning of the next section, is that if you change the order of the limits of integration here, instead of going from b to a of f of x dx, if you go from a to b, it's going to flip the sign of the integral. It's going to change it from positive to negative. So that's another property of our integrals. And we'll use those as well. There's a third property. It's called the additive property. Let me mention that real quick. You can write this area here. Let me see if I can't zoom in a little bit better. There we go. This area could be represented in 2 different ways. You could just integrate from a to b of f of x, and that's fine. Or, assuming that some point c was in between, then the left half of this is the integral from a to c of f of x dx, plus the integral from c to b. So notice how these two kind of fit together. You've got c here and c here. So just another property of the integrals. There's lots of them. I'm not going to get all of them in this case. Yes, sir? We won't see until the end of the next section. All right? But there are places where you want to split it up. It's a good question. Just hang on to it. Okay, so appreciate the question, Giselle. Let's look at problems like number 46. And Charlie, you'll see a little bit of an answer to your question right here, but I think we'll see the better part of it soon enough. What you're given in this one is the integral from 0 to 3 of f of x dx is 4. And at the same time, the integral from 3 to 6 of f of x dx is negative 1. Part A asks you for the integral from 0 to 6 of f of x dx. Well, conveniently, if you look at what's given up above, I could rewrite this as the integral from 0 to 3 of f of x dx plus the integral from 3 to 6 of f of x dx. The important thing to notice is how these things match. The upper limit here and the lower limit down there, they match. How does that help me out? 4 plus -1. Yeah. So 3 would be your overall area. And that's it. That's it for problem number, or part A. Charlie is a better example of where we would use that property. It's going to be when we integrate the absolute value at the end of our work in section 5.4. How about the next one? Problem number, or part B, the integral from 6 to 3 of f of x dx. Well, it's not something that's exactly given to us, but there is something related to this that's given, right? What's related is this. So if I looked at the integral from 3 to 6 of f of x dx, that's nice because I have something. But in going from here to here, I've changed the order of the limits of integration. What else changes? The sign. So that would be a negative here. Well, the integral itself, we already know. So the integral itself, right here, is given as -1. So I get the negative of -1, which is +1. Part C. Boy, I hope this is a giveaway point when something like this shows up on an exam. 0. Yep. Upper and lower limits are the same. So 0. Cool. Done. Yes.
That was easy.
Good. Put a dozen of those on the exam, right? All right. The integral from 3 to 6 of -5 times f of x dx. How can we work with this one? Any suggestions? Yeah, factor out the -5. -5 is a constant with respect to x, so it's -5 times integral from 3 to 6 of f of x dx, which is -5 times -1, which is 5. So, friendly problems. I like those type of problems. Basically it's just asking you, do you understand some of the fundamental rules of working with integrals? That's all. It's not trying to trick you. Yes, sir.
Reminds me of from college algebra where they give you this really complicated meaty problem where it'll be raised to the 0 power.
Oh yeah. Raises 0, right.
So it will always give us explanation.
Well, I mean, this is just one way to ask different types of problems. Eventually, what our goal is to be able to calculate stuff like this ourselves. Now, let me remind you, we'll do one last problem. It's problem number 6, to remind you of what a royal pain it is to calculate these areas. Because right now, we got to go through this really tedious limit process. So, the reason I want to go through this is so that you're going to feel like rapture when we get the fundamental theorem of calculus, and we can do this thing in about a minute as opposed to 10 or so minutes that it takes now. Okay, so one last one from this section, and it's problem number 6. Are we good on the last one? There. You know what? There's actually going to be one more we get to before we do that one, or before we finish up. Let's stick with. We'll do problem number 51 first, and then I'll go do the tedious long calculation. That'll get us out of this section. So problem 51. Let me draw myself a nice little graph. Okay. So this little button comes in handy for more than just some fun. There. And let's see. About there. Okay. Oh, sorry. So I'm just drawing a little height here. This is problem number 51 in the book. It's easier for me to show it here than it is for me to fold my book down on the screen. So that's why I'm drawing it. You don't necessarily need to copy all of this. It's mostly the left-hand part that we're going to need. Okay, so here's our function. Call it f of x. Y equals f of x. And let me label some things. This is the point 0, negative 2. This is the point 4 and 2. This would be negative 2 and 0. This would be negative 4 and negative 2. I think that's all we need. I guess it might be implicit, maybe not, but that's 2 and 0, and then that would be 6 and 0. This is another area type problem. You're going to be asked in part C to calculate the integral from negative 4 to 2 of f of x dx. So what's that mean? Well, essentially, we've got two areas here. Get area 1 and area 2 here and here. So that's area 2. We want to find the area of these because that's what we're asked for. We're asked to integrate this from negative 4 to 2, which means finding these areas. That's going to be a little bit more than just finding those areas. We have to take account of the fact that these areas are below the x-axis. So one way to view this problem is to say, all right, well, this is the same as the integral from negative 4 to negative 2 of f of x dx plus the integral from negative 2 to 2 of f of x dx. So Charlie, I'm using that little theorem that I told you about. This is kind of a manufactured use. We'll see a better use coming up. What should I write down for this area? How would I calculate that area? Yeah, base times height. So the base here is a distance of 2. The height here is a distance of 1. So 1/2 base times height is going to be 1/2 of 2 times 1. So 1. But should I put in a 1 for A1? Should I put in a 1 there? Amelia? Should I put in a 1 there? Does 1 work? 1? No? What should I put? Some help? Negative 1. Because the area is below the x-axis. Alright, so we'll put in a negative 1. How about this one? What area should I, or what should I do to calculate this area? A2. Go ahead.
Pi r squared times 1/2.
Good. 1/2 pi r squared. In this case, what's the radius? 2. So 4 pi times 1/2 is going to be 2 pi. Plus negative 2 pi. Overall, our answer is going to be negative 1 minus 2 pi for the integral from negative 4 to 2. I think part D asks you to extend this to A3. So if you had to integrate from -4 to 6, -4 to 6, then you'd have to add the area that you get for A3. Now the area that you get for A3 would be a positive area. I'm just going to calculate it again as the area of a triangle. One last one regarding this, and this is kind of setting up some work we're going to do later. I think part E asks you for the integral from -4 to 2, or let's just, maybe it's not part E, it's similar to part E, of the absolute value of f of x dx. What's the absolute value going to do to the graph here? Yeah, it's going to make it positive. So instead of having something below the x-axis here, it's going to be above the x-axis, like this. And likewise with our semicircle, it's going to get reflected above. How would that change my answer if I was working with the integral from -4 to 2 of the absolute value of x? Absolute value of f of x, I should say. Yeah, these would be positive values now, right? Because the areas would be above the x-axis, so it would be 1 plus 2 pi. So that's the change it would make. This is still going to be above the x-axis even after you take the absolute value, so that's not going to change. But the other two parts are going to get reflected above the x-axis. Okay, so the last little piece about section 5.3 then is to go back and look at problem number, you know what? Let's see, is it problem 6 that I want to do? Yeah, we'll do problem 6. The integral from 1 to 4 of 4x squared dx. So this is another area problem. Essentially it's finding the area between 1 and 4 on the x-axis, under this curve, and above the x-axis. So right now the only way we know how to do that is through that limit process. That really tedious, long, super fun limit process. It starts out with finding the width of our subintervals. Delta x is b minus a over n. What are b and a in this particular problem? Thank you. 4 minus 1 gives me 3 over n. That's going to be the width of each of the little rectangles that I use. So that's our width. I'm going to need to find the height. Before I find the height, I need to figure out where I'm going to find the height. The height comes from the function, but I need to figure out where I'm going to evaluate the function in each of my subintervals. So just as kind of a reminder here of what this all looks like, let's dial this down to something a little bit more sane. Even that's a little bit much. Too far. Come on. There. So delta x, that's the width of these. The height depends on where you want to calculate it. These are calculated as the left-hand endpoint. So the y-coordinate at the left-hand endpoint. Let's move back over here. C sub I is going to be a plus delta x times I. In this case, 1 plus 3 over n times I. And now I want to find the height. The height is the value of the function at this point. So f of c sub I is really 4 times 1 plus 3i over n quantity squared. Now just as a quick aside, on the last test, I saw a lot of this kind of stuff. X plus 3 squared is x squared plus 9. Not true. You can't square this out by just squaring the terms. There's a middle term, a cross product term. So let's be a little bit careful squaring this out since it's not exactly the simplest of expressions. The 4 is going to stay out in front. I'm going to multiply 1 plus 3i over n times 1 plus 3i over n and FOIL this all out. One times 1 is 1 plus 3i over n twice you've got like terms in the middle that you can combine. So that's 1 plus 6i over n plus 9i squared over n squared. Should be a squared here. And finally, I'm going to distribute the 4. So equals 4 plus 24i over n plus 36i squared over n squared. Yes, looks good. Keep in mind what this is. This is your height. Now, it's not always going to be quite so tedious to come up with that expression, but there's a little bit of extra work for us in this one. We've got the height and the width of each of our little subrectangles. I'm going to use the height times the width to find the area of one such rectangle and then clean up that expression. Are we okay up to here? Give you a chance to catch up, shake off your hand, get the writer's cramp out. Of course, you're in mid-season form by this point in the semester, but it's all right. So let's find the area of one rectangle. Area of one rectangle is going to be the height times the width. Let me pull those two expressions together. It's going to be 4 plus 24i over n plus 36i squared over n squared times 3 over n. And we'll simplify that product. Basically, we're just going to distribute the 3 over n. 12 over n plus 72i over n squared plus, that'd be 108i squared over n cubed. Yay! Little milestone. As I grade your papers on these types of problems, I set up little milestones for myself. You know, do you get the right expression for the height? Do you have the right expression for the width? Do you have the area of one rectangle? What comes next is adding up all those rectangles. So let's add up the area of all those rectangles. Here's our expression right here. So if I add up the area of all those rectangles, leave a little space here. It's going to be the sum from I equals 1 to n of 12 over n plus 72i over n squared plus 108i squared over n cubed. Right now, this is just an approximation. It's an approximation because no matter what the value of n is, it's just a finite number. So it's just like here having 4 or 37, etc. It's not an exact number until I take the limit as n goes to infinity. So let's make this an exact number, an exact area, by taking the limit as n goes to infinity. Limit as n approaches infinity of this, and that will be my area. Basically what's happening is you're making those intervals get really, really, really small. And as they do, the error you make in using this sum to estimate the area goes to 0. All right, almost done. If you're with me at this point, bonus points. I know this problem's pretty tedious. Some of you are more interested in your hair, and that's how I understand. Well, here's what we're going to do. We're going to split up this sum into a bunch of smaller sums. Oh, that was a joke. I don't really want you to write that down. So, you can. Don't let me stop you. I mean, they're your notes. Treasure them. Sell them on eBay when you're done with the course. Sum from I equals 1 to n of 12 over n plus 72, I suppose 72 over n squared times the sum from I equals 1 to n of I. Let's get rid of that. Plus 108 over n cubed times the sum from I equals 1 to n of I squared. Notice that the properties of the summation parallel a lot of the properties that you've seen with the integral. Liam, maybe you can help me out here. These sums are going to get a lot simpler real fast. What could I put in here? What could I replace this with? Actually, this is actually a constant. So it's just the number times the constant. So it's n times 12 over n. All right. The formula you're thinking of is over here. For 72 over n squared, go ahead. Sum of the first n integers is? Good. Someone be a show-off and do the last one. Sum of the first n squared integers. What was that one? Well done. All right. Now it's at this point that it's helpful to check yourself. Now how did I suggest you could check yourself? Yeah. These exponents should be equal. So first power and first power. Second power, second power. Third power, and multiply it all out, you're going to get a cubic up there. So they match. That's real good news because this is a long problem. You don't want to get down here and go, wait a minute. This is an n squared, this is an n cubed. If you had something like that, then your limit's going to go to infinity. That's real bad because you're going to get a finite area, not an infinite area. What can we do here? Well, we get some nice cancellation with these. The n's disappear completely. So I get the limit as n approaches infinity of 12. And I'm going to get some cancellation here. 2 goes into 2 once and into 72 36 times. I'll also get rid of one of the n's. That one there cancels with the squared, leaving me just an n. Some more cancellation here. 6 goes into 36, 6 goes into 108, 18 times. So I'll have an 18 here. And like before, I can cancel out one of the n's. That'll cancel out one of these, leave me with an n squared. Oh my. So, at this point, anything that makes this process simpler will be really, really welcome. 36 times n plus 1 over n plus 18 times, that'd be 2n squared plus 3n plus 1 over n squared. Whew. Like that. Last but not least, We can finally take the limits. Notice I've been consistent in all these. I wrote the limit with all of those. We can't just leave off the limit. These things aren't equal to our final answer without the limit. So let's take the limit. The limit as n goes to infinity of 12 is just 12. What about this limit here? As n goes to infinity, what happens to this? Limit is n plus 1 over n. It's 1. Why is it 1? Yes, perfect. This is n to the first power, n to the first power. Their degrees match. So if their degrees match, then it's just the ratio of the leading coefficients. Leading coefficient there is 1. Leading coefficient here is 1. So you get 1 over 1. So 36 times 1. Plus 18 times what? 2. 36 is 72, plus 12 is 84. Whew! Wow. Grab the oxygen bottle. Shake your wrist out. Okay, so this is a reminder of the long way that we have to calculate these things. So let's finish this section up now. In fact, we are done. For homework, try 3 through 47 and 51. So section 5.3, 3 through 47 and 51. Let's make this process of finding these areas a lot easier.